shaft here, with spring-like structures at each end that allow greater flex or minor misalignments between the engine and transmission. This also keeps sensitive parts in the engine and transmission from imparting harmful vibrations to each other. This is where the drive shaft connects to the transmission. Power travels through a set of bevel gears, reducing input RPM or rotation speed. A hollow shaft connects to a planetary gear set above. Planetary gears allow further RPM reduction, but are also very strong while keeping a small form factor. The bevel gear drives the central sun gear. Power flows from the sun gear to smaller planetary gears, which are mounted in a planetary carrier. This is where the main rotor mast connects to the system. The mast extends from the bottom of the transmission upwards all the way to the top of the rotor assembly. Splines at the planetary carrier drive the mast. If the drive shaft entering the transmission is spinning at 6,300 RPM, these gear sets have reduced rotation to around 400 RPM at the rotor. The transmission is mounted with a 5-degree forward tilt, so the cabin sits level during forward flight, and a 1-degree left tilt to compensate for translating tendency, which is a helicopter's natural tendency to drift right from slight tail rotor thrust effects as it works to keep the aircraft from spinning. Mounts are made from rubber-like materials designed to absorb vibration. There are springs at each side that extend from mounting pylons to the transmission case for the same reason. Having seen the transmission and main rotor mast, let's trace power backwards from the engine. With a zoomed-out view, you can see that the drive shaft is not entirely straight, but is divided into sections between components and along the tail boom to